So, last time we have considered the theory of flat plate collectors, particularly the liquid heaters, which will consist of an absorber with tubes attached at the bottom. Subsequently, we have shown that the temperature distributions in the direction of x a constant over the region of the tube and with a maximum at the middle of the plate in between the two tubes. This is temperature axis, this is the x axis. Similarly, if we want to have temperature at any fixed x, it changes with respect to y, fixed x, and this is T. This may be in general T anywhere on the plate, and the corresponding fluid temperature will be a bit lower than that, depending upon how efficient the heat transfer mechanism is. Then we have gone through the analysis considering a repetitive element of a tube and half a plate on either side, with the distance being W. Let me draw it bigger. There may be an inside diameter d I and outside diameter d. This is the repetitive element, and this distance is W minus d by 2 if the diameter is d, and this is at a temperature of T b, and this is bonded by soldering or welding to the tube. We have subsequently considered an elemental volume in the, let us say, the fin area. The mid plane, since the temperature is maximum, can be considered as insulated, with the element being shown of elemental length delta x. In general, this is receiving the solar radiation, and it will be losing also heat by a loss coefficient times T p function of x minus T a. This p is unnecessary, it is a function of this, and the thickness of this is delta, not to be confused with the declination. They do not appear at any time the same time. So, we have set up that a conduction heat transfer of k delta dt dx enters at x and leaves as k delta dt dx at x plus delta x, which is nothing but minus k delta dt dx plus d by dx of minus k delta dt dx evaluated at multiplied by delta x. In the limit, we made an energy balance of the incoming radiation delta x, and then a loss u l times delta x into T function of x minus T a plus minus k delta dt dx at x should be equal to minus k delta dt dx evaluated at x plus delta x. So, this is written as a balance equation incoming radiation is the absorbed energy multiplied by delta x and a unit length perpendicular to the plane of the paper minus the losses over the same area, and what enters is minus k delta dt dx, and what finally goes out is minus k delta dt dx at x plus delta x. This quantity if you take the limit and express k delta dt dx at x plus delta x, you will get an equation of d squared t by dx squared equal to u l upon k delta times T minus T A minus S upon U L. You can check, all of them have the same dimensions of temperature, and the two boundary conditions would be dt dx at x is equal to 0 and t at x is equal to w minus d by 2, that is at the base of the pipe or the tube will be equal to T b. And of course, we define the parameter u l upon k delta as m squared and psi as t minus T a minus S by u l. So, this simplifies to an equation d squared psi by dx squared minus m squared psi equal to 0 with d psi dx at x is equal to 0 as 0 and psi at x is equal to w minus d by 2 should be equal to t at the base minus T a minus S upon u l. Now, this equation should ring a bell. You must have come across in your heat transfer course. This is nothing but a Finn equation, and you will find that the parameter m squared equal to u l by k delta, whereas in the conventional Finn equation it is h perimeter upon k a. You can see both of them are non-dimensional. H corresponds to u l and k is k. Instead of one length dimension in the denominator, you have a length and a square of the length in the denominator in the conventional Finn equation. This is absolutely the same as the Finn equation, which you must have gone through in your heat transfer course. The general solution for psi will be C sin hyperbolic m x plus C 2 cos hyperbolic m x, and if you apply the boundary conditions that dt dx is equal to 0 or d psi dx is equal to 0 or psi equal to T b minus T a minus S by u l, you will obtain the temperature solution as T minus T a minus S by u l by T at the base minus T a minus S upon u l as cosine hyperbolic m into x by cosine hyperbolic m into w minus d upon 2. So, now we got the temperature distribution in the x direction at a fixed y, and if you look at the contribution from the fin, that is from the plate or fin to the tube, should be equal to 2 times minus k delta multiplied by unit length perpendicular to the plane of the board or paper, evaluated at x is equal to w minus d upon 2, and this 2 comes from, there are 2 halves, 1 plus 1, that becomes 2. So, that if you evaluate, you will have a w minus d times s minus u l times T b minus T a multiplied by tan hyperbolic m into w minus d upon 2 whole thing by m into w minus d upon 2. So, m being non-dimensional, so this entire quantity will have a length dimension, right. So, this can be rewritten as w minus d times f times s minus u l into T b minus T a. Now, you will find that f is tan hyperbolic m times w minus d by 2 upon m into w minus d by 2. Right, and this f, now we call it the fin efficiency. So, it depends upon m, which contains the loss coefficient, thermal conductivity, and the distance between the plates, w minus d by 2. Now, recall if there is a length of fin of length L, the fin efficiency is defined by tan h m L upon m L for a certain boundary condition of negligible heat transfer from the tip, f is equal to tan h m L by m L, which is exactly similar to what we got for the fin and tube type of absorber. Now, the total energy gain also will comprise of the energy gained from the tube region, which will be S minus U L into T b minus T a. We assumed that there is no temperature variation on the periphery of the tube. So, that will be the same as the base temperature T b, and d is the projected length and multiplied by the unit length perpendicular to the plane of the paper will be the corresponding area. So, q dash tube per unit length of the collector will be S minus U L into T b minus T a times d. Now, useful energy gain should be comprising of what came from the plate region plus what is gained from the tube region which when combined will give me nothing but w minus d times f plus d times S minus U L times T B minus T A. Now, the same Q U dashed is transferred to the fluid. So, T B, if it is the tube temperature, and T F is the fluid temperature, my Q U dashed should be transferred with a potential of temperature difference of T B minus T F upon the convective resistance pi d I H F I plus a resistance due to bonding between the tube and the plate. D I is the inside diameter of the tube, and H F I is the heat transfer coefficient in the tube. If the flow is laminar and fully developed, you have a 3.66 for constant temperature and about 4.12 for constant heat flux, but the situation is neither constant heat temperature or constant heat flux. So, it should be something in between, and the bond conductance C B is given by thermal conductivity of the bond material, by the width of the bond material, thickness of the bond material, and gamma is the thickness. K B thermal conductivity of the bond material, and B is the width, and gamma is the thickness. Once again, this gamma is not to be confused with the azimuthal angle. Of course, they do not appear side by side simultaneously. Now, let me explain a little bit about this width and the thickness. If this is the tube, and I may put it like this, which may be equal to the diameter or it may be less than the diameter. So, this is my sort of width B, may or may be less than diameter or greater than diameter, and the thickness, one way to define it is make an equivalent material, this thickness will be gamma. In other words, if you have used a certain amount of material over a width of B with varying thickness depending upon the contour of the tube, it may be equivalent to the same material of width B and thickness gamma. So, we equivalently evaluate the bond resistance by this method. So, if we equate Q U dashed what is transferred to the fluid and what is coming from the plate plus the tube region, then and eliminate T B. We do not want to have T B. So, now I have something like an area W multiplied by the unit length perpendicular to the plane of the paper will be the area, and that F dashed whatever we were defining earlier as the collector efficiency factor multiplied by absorbed radiation minus the losses taking place from the local fluid temperature to the ambient. and here if you equate those two equations, f dash turns out to be 1 upon u l by w 1 by u l times d plus w minus d into f plus 1 upon the bond conductance plus 1 upon the convective conductance. Now, you will find f dash brings in geometry by w, w minus d, etc. And through f, it is the material plus the heat transfer coefficients. C b, how good the bond is, and of course, this HFI is an indicator of fluid and laminar, generally laminar or turbulent flow, or at times we may do something to enhance the heat transfer coefficient inside. So, that this pi di HFI will be large and 1 by pi di HFI will be small. The resistance due to convection will be small. So, now one can interpret this actual useful energy gain. So, f dashed by energy gain if the collector is at local fluid temperature. Now, another interpretation is possible. Now, we have got 1 upon u l by this quantity, that is w times 1 upon u l into d plus w minus d times f plus 1 upon C b plus 1 by pi d I h f I. Let us for a moment imagine f is equal to 1. It is a 100% fin efficiency and C b is bond conductance very high. So, that 1 by C b tends to 0. Similarly, one by pi d I h f I also goes to 0. If you have a very large heat transfer coefficient, the convective resistance will be negligible. So, my f dashed tends to 1. So, this term is 0, u l into I think this should be w. So, you will have f dash tending to 1 if this bond conductance is infinity and if the convective resistance is 0. So, this u l gets cancelled and f dash will turn out to be equal to 1. Or one can write down 1 upon u l divided by 1 upon u naught, which can be rewritten as u naught upon u L. This is resistance from plate to ambient by resistance from fluid to ambient. So, F dash is not only the actual energy gain upon the possible energy gain if the entire collector had been at the local fluid temperature, but it also can be defined as the resistance from plate to the ambient to the resistance from fluid to the ambient. So, now we got out of the two one dimensional equations, temperature distribution along the x direction has been obtained. From that, the fin efficiency comes into the picture, which will tell you whether these tubes are pretty close to each other or far off. So, that my fin efficiency will be lower because W minus D will be larger. And of course, the material comes into the picture, the thermal conductivity, and finally, the energy transfer to the fluid will take into account the heat transfer coefficient H f I. So, at a particular y, fixed y, we know how the temperature varies on the plate in the solar collector. Now, we will go for temperature distribution in the flow direction. One of the important things that we have to remember before we go into this, F dashed is valid for a certain fixed y. So, in principle it can be changing with respect to y, or one may define a particular average sort of F dash depending upon y chosen. But now, if we find the temperature distribution in the flow direction, first only we may concentrate T f changing from initial temperature T f I with which it enters to the exit temperature T f O. Since we know the fin efficiency, bond conductance and the convective resistance, T p or T b can be calculated. From T b, T at any other x can be calculated. So, we shall concentrate on the energy balance on the fluid element inside the tube. So, we consider the tube, again take a control element of length delta y now. So, this will receive q dashed useful times delta y. What gets in is mass flow rate divided by the number of tubes multiplied by specific heat and the fluid at y. What gets out is m dot by n C p and T f at y plus delta y, and this is the delta y elemental length in the direction of the flow inside the tube. So, it is receiving a q dash useful times delta y, and energy at any particular y, if it is entering at the temperature of T f, the temperature is one can imagine to have been augmented to T f at y plus delta y, indicating the energy gain from the solar energy. So, if we make the energy balance, you will have a simple first order differential equation. We have used the QU equation, and we also have used T f at y plus delta y will be T f at y plus T T f by d y times delta y in writing the balance. In other words, we wrote m dot C p T f at y plus this q u dashed delta y should be equal to m dot by, of course, there is a n C p T f at y plus delta y, where q u dash we already know as equal to w times f dashed. S minus u l into T f minus T a. So, this we know, if we substitute in that equation, we have the first order equation m dot C p, again let me repeat, the one boundary condition that you will be requiring will be T f equal to T f initial at y equal to 0. The temperature at which the fluid enters is the boundary condition needed here. So, it is simple to integrate, it is a first order equation only. So, you can, and T a and S are assumed to be constant along with your U l, T minus T a minus S upon U l by T f I minus T a minus S upon U l will be exponentially decaying U l n W f dashed y by m dot C p. Okay. So, the temperature, as a matter of fact, it is T f. So, T f changes according to y depending upon the overall loss coefficient, spacing, number of tubes and the mass flow rate. M dot by n is nothing but the mass flow rate per tube and the C p. So, if I want to estimate my exit temperature, T f o is nothing but T f at y equal to L. If L is the length of the solar collector tube, then at y is equal to L, T f will be the exit temperature T f o. So, that is given by T f o minus T a minus S upon U l upon T f I minus T a minus S upon U l should be equal to e to the power minus A c U l f dashed upon m dot C p. A c you will realize is nothing but n W into L. If L is the length of the tube and W is the width times n, that will be the total collector area. Now, you may have this A c by m dot is nothing but in the denominator m dot by A c. So, you may have m dot by A c the flow rate per unit area. Some books may write it like that, a G instead of A c in the numerator and m dot in the denominator. So, now what do I have? I know how the fluid temperature varies from inlet to the outlet. and I can estimate the outlet temperature, and we have already found the variation in the x direction through the fin concept. Now, having done this, we shall now estimate heat removal factor FR, and to one more factor, the so called flow factor. You again remember f dash is evaluated, the collector efficiency factor. Now, we are about to find out the heat removal factor F R, that originated from our basic equation Q u, useful energy gain from a collector of area A c as incoming radiation, multiplied by an effective transmittance absorptance product minus the losses taking place from the plate temperature to the ambient, which has been successfully, rather subsequently, modified as A c times collector efficiency factor f dashed into I t tau alpha minus U L into T f minus T a. That means, as if the losses are taking place from the fluid temperature rather than the plate temperature. To compensate this underestimation, we have put a factor f dashed, which will be less than 1. Subsequently, we set even the uncertainty of this T f, whether it is the mean temperature or the temperature of the fluid at a mean location. A heat removal factor has been introduced, F r minus U L, the minimum possible loss from the collector will be at the minimum temperature T f I. So, you compensate by again the second factor, the heat removal factor F r. So, now if I try to express heat removal factor F r irrespective of collector energy gain equation, the actual energy gain by the collector is truly mass flow rate multiplied by the specific heat multiplied by temperature difference between the exit and the inlet upon the energy gain if the entire collector had been at the inlet temperature of the fluid minus T a. In other words, this is a maximum possible energy gain by a collector compared to the actual one m dot C p into T f o minus T f I. So, this can be rewritten as m dot C p by A c times U L T f o minus T f I to bring it to the standard form S by U L minus T f I minus T a. So, this can be again rewritten, it is a simple algebra, but so add and subtract T a minus S upon U L minus T f I minus T a minus S upon U L, because we know that ratio. That is exactly the reason why we are trying to express in this fashion upon A c U L times S upon U L minus T f I minus T A. Okay. So, F R will be, if I take out the common, m dot C p by A c u l times 1 minus S by u l minus T f o minus T a by S by u l minus T f I minus T a. So, this is simply m dot C p A c u l times, from the relation which we have got for T f o minus T a minus S by u l by T f I minus T a minus S by u l, 1 minus e to the power minus A c u l f dashed by m dot C p. So, if you look at this particular equation, heat removal factor, in addition to containing f dashed and the loss coefficient, right, f dash contains the thermal conductivity of the material, spacing of the tube, geometry in general, it contains an additional factor m dot. So, the flow rate indirectly is going to influence your heat transfer coefficient, even if that is not very significant unless the regime changes from laminar flow to turbulent flow. You have got the effect of higher m dot reflected in F r. That is, if indirectly m dot is high, my delta T or T f o minus T f I is low. If you send a large flow rate through the collector, you will have the temperature increase to be smaller. So, the T operating, if I try to call it that, is low. So, losses are less. So, this implies my heat removal factor will be higher if the flow rate is higher. That may be due to an improvement in the heat transfer coefficient, or a direct effect of higher m dot is to have a lower delta T and hence lower losses. Now, people have introduced another factor, flow factor, which is f double prime equal to f r divided by f dashed, which will be m dot C p A c u l f dashed times 1 minus e to the power minus A c u l f dashed by m dot C p. So, if you look at this, this is nothing but some sort of a beta 1 minus e to the power minus 1 by beta. So, obviously, this should be a non-dimensional quantity. So, the flow factor of any collector is simply the mass flow rate, overall loss coefficient, area, and the collector efficiency factor. F double prime is a function of only this quantity. For lack of a better name, we will call it the dimensionless flow rate. So, the flow factor is a sort of non-dimensional flow rate function. Now, if you look at finally Q has been expressed as AC FR times IT tau alpha minus UL into T of I minus T A, where Fr is the heat removal factor. More in another notation, we may write it as SR into S is the absorbed energy minus UL into, we will drop that fluid T F I minus T A, which simply is written A C F R S minus UL into T I minus T A. In other words, there is no confusion about the inlet temperature. A fluid inlet temperature is unnecessary, most of the time T I used. This is most commonly used equation. It is originally due to Hotel, Wheeler and Bliss of MIT, and the interesting feature is this is based upon simple two one-dimensional equations, and there have been comparisons with two-dimensional approaches for the collector using finite difference method, finite element method, and you will find that the difference has not been more than 5 to 5% or so compared to this simple equation. So, this remained a very popular equation still being used in spite of the assumptions that we made in calculating or expressing these quantities. Now, so far we found the useful energy gain, which to our satisfaction related to the geometry, meteorological data, material properties, including thermal conductivity and the transmittance absorption product, flow rate more importantly, equally importantly, we got it. Now, there is a efficiency F dashed is the collector efficiency factor, but this is not efficiency of the collector. Okay. In principle, one can make F dashed can go to 1. For example, if I have tube to tube, a large number of tubes, this F dash will tend to 1, or for let us say air heating collector, this may be only a duct with the flow perpendicular to the plane of the paper, and here also the fin efficiency is 1, F dashed sorry, this will be fin efficiency equal to 1. Consequently, your F dashed also will be higher. So, this is only to emphasize that your collector efficiency factor is not an efficiency. So, we will try to find out what is the efficiency of the collector and how do we define, and absorbed energy is tau alpha into I t, which can be rewritten as tau alpha into I into that global conversion factor R. What is the input is I t. So, I may define efficiency to be useful energy gain upon the input I t. So, this will be F r tau alpha minus F r u l times T I minus T A upon I t. So, this can be written already it is in the same form. We should only remember in calculation of efficiency also, this should be interpreted as minus that hidden time factor comes into the picture depending upon the time. This is for joules per meter square during delta t. Otherwise, this will be watts per meter square, this will be joules per meter square integrated over a time delta t. So, this is one mistake that is commonly done, do not do that. Now, if you look at it, eta decreases linearly with T I minus T A upon I t. If you look at this parameter, if the temperature difference is large, my efficiency will be lower, which means the operating temperature is higher. Then if the incoming radiation is high, the losses will be a part of the incoming radiation. So, my efficiency should be higher. So, this seems to be a good parameter, which of course, the equations gave. Of course, this is true when U L is constant, right. So, eta decreases with the parameter T I minus T A upon I t linearly if the overall loss coefficient is small. In general, by experiments find efficiency, fit a best line, a linear variation, and not bother much for high T I minus T A by I t when U L is not a constant. So, we assume that the collector will be operating at reasonable values of T I minus T A upon I t. One can have an idea of the numbers when we solve some exercises, and you do not go to a very large value of T I by T A by I t. So, that variation of U L makes the efficiency variation nonlinear, not because of you are afraid of the nonlinearity, but the efficiency will be low, consequently effectiveness of the solar collector will be small.